Look around you. Everything you see, the screen, the infrastructure, the very chair you sit on, is a product of a single, highly specialized evolutionary outcome. We call it intelligence. But what if the defining characteristic of our species was not an inevitable climb, but a series of profound, irreversible biological accidents? This is not a story about how we became smart. It's an investigation into why the universe rarely attempts such a costly experiment. For too long, we have defined intelligence anthropocentrically. We measure it against human metrics: tool use, language, self-reflection. But to truly understand its evolution, we must strip away our biases and start 540 million years ago, asking a simpler question: what is the fundamental pressure that compels a cluster of cells to process data faster? The journey from simple sensory detection to complex abstract reasoning is marked by three critical transitions. First, the neurological specialization; second, the energetic bottleneck; and finally, the social amplification. Ignoring any one of these steps leaves the greatest evolutionary mystery unsolved. The first great catalyst was the Cambrian explosion. Suddenly, soft-bodied organisms evolved shells and speedy predators. This arms race demanded an immediate upgrade from passive sensing to active calculation. This intense pressure gave rise to the basic prototype of the nervous system, the ganglion. But a central brain isn't mandatory. Consider the cephalopods. Octopuses, with their astonishing problem-solving capabilities, host two-thirds of their neurons not in a central brain, but in their arms. This is a powerful lesson in convergent evolution. Intelligence does not require a singular, centralized command structure. It requires effective environmental feedback loops. So, if basic processing power is widespread, why did the primate lineage dominate abstraction? The answer lies in the shift from olfactory dominance to visual dominance. Relying on sight for complex three-dimensional navigation and social signaling demanded exponentially more computational resources than simple smell tracing. This leads us to the critical bottleneck: energy. The brain, representing only 2% of the body mass, consumes 20% of the body's total metabolic energy. To support a larger, more complex brain, our ancestors needed a guaranteed, ultra-high-calorie diet. The key innovation wasn't the brain itself, but the ability to digest more efficiently. The mastery of fire, nearly 400,000 years ago, was arguably the single most important prerequisite for human cognition. Cooked food broke down tough fibers, increasing caloric absorption dramatically and reducing the time spent chewing. This freed up massive metabolic resources, funding the expansion of the neocortex. Parallel to the caloric shift, the biomechanical shift occurred: bipedalism. Standing upright wasn't about speed. It was about efficiency and, crucially, freeing the hands. Hands became the external laboratory of the brain, allowing for complex manipulation and the feedback loop necessary for developing precision tools. We now approach the social amplification. A bigger brain alone is useless unless it is trained. As group sizes increased, so did the necessity to track complex relationships, hierarchies, and reciprocal agreements. This cognitive load is what drove the development of specialized neural circuitry for social inference. This relentless social pressure ultimately unlocked the amplifier: symbolic language. Language is not merely communication. It is a technology for externalizing and sharing computation. It allows us to offload vast amounts of data and models of reality from the individual brain into the collective mind, accelerating learning across generations. But here is where the analytical language must sharpen. Intelligence, in evolutionary terms, is a specialization, not a perfection. It is an extremely high-cost niche adaptation, much like a giraffe's neck or a whale's size. Why, then, are we the only species to have pursued this niche so far, resulting in global technological dominance? The answer lies in the concept of the cognitive runaway effect. Once our ancestors crossed the threshold of cooking, bipedalism, and social complexity, the benefits of greater intelligence outweighed its immense metabolic cost, leading to rapid, self-reinforcing selection pressure. Any slight improvement was dramatically favored. This deep history provides a crucial modern insight. Our inherent cognitive biases, our need for group cohesion, our preference for immediate feedback, our tendency toward tribalism, are not flaws of character. They are the optimized survival strategies of a socially complex primate adapted for a Pleistocene savanna. Understanding intelligence as a fragile, metabolically expensive adaptation should prompt a reevaluation of its permanence. We are currently living within the narrow climatic band that allows our complex, energy-intensive brains to function optimally. Slight environmental shifts could radically change the calculus of survival. Our modern challenges, from designing efficient societal structures to navigating geopolitical complexity, are, at their core, challenges our Stone Age brains were never specifically wired to handle at this scale. The intelligence that allowed us to create these systems is now testing the limits of its own evolutionary programming. The evolution of intelligence reveals that humanity is not the finished product of a master plan, but the beneficiary of a long series of specific, non-replicable biological lucky breaks. A shift in diet, the mastery of fire, a need for social tracking, and the invention of externalized symbolic thought. The greatest task before us is recognizing this profound fragility. We must shift our focus from celebrating the outcome, our intelligence, to analyzing the process that created it and accepting the limitations it imposes. Because only by understanding the true constraints of our evolutionary hardware can we hope to navigate the future. What evolutionary path do you believe was the most decisive factor in human cognition? Was it fire, language, or perhaps social pressure? Let us know your analysis in the comments below. If you found this investigation valuable, please like and subscribe for more deep dives into the mechanisms that shape our existence.